What's up, Simpsonites? It's game time. And by game time, I mean it's another late night Sim Science recording session. Okay? We're getting into some fun stuff here. Okay? The sport of chemistry, the art that is chemistry. Okay, we're going to start flexing on these problems with some serious conversion factor equivalency knowledge. Okay? So, this is a poor attempt to recreate the handout that you have now in front of you. I tried to copy it over to this format. It was extremely blurry and it was making me angry, so I just wrote the whole thing out. Not the easiest thing. Okay, so in this video, we're going to fill out the conversion factor side of this chart. I'm also going to add a lot of notes in throughout the entire chart. So write down, ideally probably in your own words, pretty much everything I'm writing down. Emily De Leon, shouts out Emily. She flexed on me earlier with this. Her method was to watch the whole video and then go back and try and fill in the notes as much as she could on her own. And I think that's a great way to try and crystallize the knowledge in your mind, making sure that you have to recall and put this out. And if you get stuck, then you go back and check. So that's a good method too. All right, so what are we talking about here? First of all, let's start with equivalency, top left up here. Okay, equivalency just means things are equal. Okay, things are equal. So, I mean, I don't really know how to go deeper on that. Things are equal. But as we're talking about this stuff here, a lot of times I think it's more helpful to use the word per. So you have this many of this per this. I think that's kind of more intuitive than saying equals for some of this stuff. And that's kind of where conversion factors come in. So conversion factors, oftentimes referred to as CFs, conversion factor CF. That's where you get the per coming in, and we'll see that throughout. If you're kind of not getting what I'm saying, you'll see it throughout. So first, let's start off with atomic mass. So atomic mass is for one element. Okay, for an atom, of a specific element. Your atomic mass equals 1 mole, and we've seen this on the periodic table. You take your atomic mass, and it's very important that this is in grams. Your atomic mass in grams is going to equal 1 mole of that substance. Okay, so for something there might be 20 grams per 1 mole. So when we write that in a conversion factor, the equal sign here, and you can do this if you want, you don't have to. The equal sign becomes the division sign of the fraction. I don't know if that's the right word for it. So you have the atomic mass per 1 mole. Okay, and mole can be, the abbreviation for mole is just take off the E, so you might see me do either one, just so you know. Or 1 mole per atomic mass. Okay, so it's interchangeable. It's a conversion factor. It's interchangeable. You have your atomic mass equals 1 mole, and 1 mole is going to be the atomic mass. So if you have something that has an atomic mass of 20, and I say you have 2 moles of it, that means you have 40 grams. If I say you have something with an atomic mass of 20, and you have 60 grams of it, then you have 3 moles. Okay, this conversion factor can be flipped to solve equations and go between atomic mass and moles, or grams and moles. So we'll get into that more. Right now, the point of this chart is really to start breaking down our conversion factor, something to reference back to as we go through these equations. So let's go on to molar mass. So what's the difference here? Molar mass is for compounds and molecules. So not just one element, but an entire molecule or compound, again, in grams. Okay, so pretty much the same idea here. Any compound or molecule is going to have a molar mass, and that molar mass in grams will equal 1 mole. So we have molar mass per 1 mole. The molar mass of a substance equals 1 mole of that substance, or 1 mole per molar mass. Okay, so obviously you can flip these conversion factors. That's how we can use them as conversion factors. Are interchangeable. We can use them for anything. So on that same train, let's go down here. We got 6.02 times 10 to the 23rd, one of the greatest numbers ever. Goes down, definitely top 5 numbers all time. Avogadro's number. All right, we know what this is. Okay, so this is telling you that if you have Avogadro's number of particles. Now, particles can be atoms. It can be molecules. It can be compounds. Okay, particles can be anything. That's what we learned in that video. It could be basketballs. It could be jelly beans, whatever. In chemistry, obviously, it's going to be atoms, molecules, and compounds. So we already know this, and Avogadro's number, 6.02 times 10 to the 23rd of anything, is going to be a mole of that thing. Okay, so 6.02 times 10 to the 23rd per 1 mole. And I can put particles here, particles, and just do P next time. Or 1 mole per 6.02 times 10 to the 23rd particles. Okay, so again, these three are really saying the same thing: atomic mass for elements, molar mass for compounds, and then Avogadro's number of particles, of atoms, of molecules is 1 mole. Okay? Now this next one is kind of tough to represent generically, so let me try and be as clear as I can about what I'm talking about here. So first of all, one important thing to add here is that this is from a balanced equation. Okay, so this is something I've talked about a little bit before. So A and B here are chemicals, different chemicals, okay? And the numbers are coefficients, okay? So you have different numbers and you have coefficients in front of them. So this is a balanced equation. So you have for X moles of A, you have Y moles of B. That's what this is trying to say. So if I had, I think I could probably fit in here. So if I had, let's say we're making ammonia. So we have nitrogen, which is a diatomic, combining with hydrogen, which is a diatomic, and it's forming NH3. So this will be balanced as we need 3 here, 2 here, and then it's balanced. So, and then we have our imaginary 1 here. So these are our coefficients, right? Now, what this is saying is that in this example, for every 1 mole of diatomic nitrogen, now this is something to emphasize when you have N2, it's 1 mole of diatomic nitrogen, so it's doubled, but we'll get to that. For every 1 mole of diatomic nitrogen, we're producing 2 moles of ammonia, NH3. For every 3 moles of diatomic hydrogen, we're producing 2 moles of NH3. So this is a ratio. Okay, so this is just saying, this is where I'm saying I think the per is better than the equal sign. So for the number moles of A, whatever number mole of A per number mole of B, and then again we can always flip that, or number moles of B per number mole of A. So if we made this 1A and this 2B, it would be for every 1 mole of nitrogen, for every 1 mole of diatomic nitrogen, we have 2 moles of NH3. And for every 2 moles of NH3, we have 1 mole of diatomic nitrogen. So that's what that means. It's not saying that the equal sign doesn't mean that it's the same number. It just means it's a consistent ratio. In a balanced equation, a consistent ratio. That's how many moles you need to produce something else. It's like and we'll get into limiting reagents later on. I'll just leave that example for later. Okay, so next one. We're talking about gases. Okay, this is for gases. Gases has 2 S's, I think. So a mole of gas, 1 mole of gas takes up 22.4 liters. 22.4 liters. Okay? And I'm going to make a note here that this is at STP, which means standard temp and pressure, because you can change this law by changing the temperature and the pressure, etc. But in general, for gases at standard temperature and pressure, they're going to take up 22.4 liters. So 22.4 liters per 1 mole, or 1 mole per 22.4 liters. Okay, so for gases, 1 mole of gas takes up 22.4 liters. 2 moles of gas would take up 44.8 liters. That's what this is saying. Okay, getting there. Okay, so anything that contains both numbers and units can be interchanged. Okay, now this is substance specific, so it depends on what you're looking at. It can be solids and liquids, so you can go from a density unit of solids to liquid measurement, volume measurement, like milliliters. So for example, let's look at CO2. Okay, if that is 1.98 grams, that equals 1 milliliter. That's its density conversion. Okay, so water is real simple. Water is 1. That's what this is all based on. 1 gram of water is equal to 1 milliliter of water. But for something like CO2, for example, 1.98 grams equals 1 milliliter. So in general, this is your number of grams per 1 milliliter. So it's different for different substances, or 1 milliliter per a certain number of grams. So for CO2, it would be 1.98 grams for every milliliter, and 1 milliliter for every 1.98 grams. So we can use this to go between, if I told you that you had 16.7 grams of CO2, you'd be able to use this to figure out how many milliliters of CO2 you had, drop it like it's hot, use the conversion factor. We're going to get into that more. Again, this is kind of a reference sheet for you. Last thing, real quick, to touch on is percent composition. So your X is going to be your percent given in a problem, okay? So you're figuring out how much something makes up of a compound that it's in. So how many grams do you have per 100 grams, right? Percentage is based on 100. It's how many out of 100. So X grams, it doesn't need a period. X grams of the part per 100 grams of the whole. Or, but equals works too, because it's saying the same thing. Or 100 grams of the whole per X grams of the part. Okay, so that is telling you a percentage is out of 100 always. So you can break that. If you have 100 grams of something, it's easy to know. If you have 100 grams of a compound and 22 of those grams are nitrogen, then you know that it's 22% nitrogen. That's what this is saying. Okay, so this is, that's the chart. It's talking about how you can use things that you know equal each other. You know that you have a certain amount of grams per mole. You know that you have a certain amount of particles per mole, Avogadro's number. Ratio, if you know a ratio that's consistent, you know how many moles of this you have per moles of this, or how many moles of this it takes to produce a moles of this, etc. The gas law, converting between something like grams and milliliters, between mass and volume. Okay, so conversion factors. We're revisiting this a little bit, and we're going to get into using this a lot in the equations that come up. So thank you guys so much for watching. Definitely like and subscribe if you want to win that iPad, which is definitely going to be given away. It's a real thing.